Metals are covered by a thin skin of oxide, and when this breaks down, you can get tiny little sites on the metal surface where corrosion starts to develop. And the problem is it's very poorly understood what the chemistry is inside these sites while they're growing. And so the highly intense beam of X-rays that you get from a synchrotron source like diamond can be used to probe inside these sites to see what's actually happening as little corrosion pits are growing. Working in this area, it's inherently a very collaborative process because a lot of the applications relate to real-world problems, whether it's to do with corrosion of biomedical implants or corrosion of nuclear waste storage canisters or problems with airframe corrosion. What we want to do is interact with people who see the real corrosion problems in practice and then translate that into a fundamental understanding of what's going on.
So the first one is that we've been looking at how the earthworms we're working on and finding at contaminated sites can actually deal with the metals which they encounter on a daily basis and which would be very toxic for normal earthworms. So at Diamond, on this beamline, we've been looking to see where the metals go in the earthworm and how they're converted into non-toxic forms. And in parallel to that, with colleagues at Cardiff University, Pete Kill and John Morgan, we've been looking at the genetics of the earthworms as well, and been able to show that these different earthworms are genetically distinct from the sort we find in the garden. So that's one of the fun things we've been doing. We've been looking at very recent and rapid evolution, over about 100 years for these earthworms to evolve to earthworms which can tolerate metal-rich conditions. The calcium carbonate that earthworms secrete contains amorphous calcium carbonate. Now the interesting thing is, if we try and synthesize amorphous calcium carbonate in the laboratory, it's stable for about 20 seconds to a minute, then it crystallizes to calcite or aragonite. The amorphous calcium carbonate the earthworms secrete is really stable. It lasts for months and months and months. And industry is quite interested in this sort of thing because amorphous materials, if you can form devices or structures out of amorphous materials, for their size, they're far more stable and strong than pieces of equipment and devices made out of crystalline material. So one of the things we're doing on this beamline with Fred Mosselmans, the beamline scientist here, and colleagues, is trying to find out why the amorphous calcium carbonate in the earthworm granules is so stable. And if we can crack that and find that out, industry should definitely be interested.
The thing about this work is it's not particularly new work, because calcium carbonate granules were one of the things that Charles Darwin was really fascinated by. So he wrote the first few papers on calcium carbonate granules, and now about 130 years later people are beginning to return to calcium carbonate granules and actually try and understand how they react with the rest of elements in the world.
Carbon capture and storage, capturing CO2 from power stations, injecting it underground, is widely acknowledged as a key component in our efforts to avoid dangerous climate change. The major public concern is to ensure that the CO2, when it's injected deep underground, stays there. So the goal of this research is to understand what happens to CO2 when it's injected deep underground, and to design an injection process so that we can ensure that the CO2 will be safely stored. Want to understand fluid flow deep underground. The rocks that we look at are rocks that are the remains of the shells of sea creatures that have died. The shells have been crushed, they've been chemically altered, and they've been deposited tens or hundreds of millions of years ago and are found deep underground, kilometres underground. We take samples of this rock and we image that rock. And it's the gaps between the bits of shell that we want to look at, because it's in those gaps at the scale of a few microns that we find the fluids. We have the salty water, we have the CO2 that we're injecting. So we take a small sample of this rock that we've collected either from a reservoir or from a quarry site. It's just 0.5 millimetre across, and we image that. We go one step further, because when we want to understand fluid flow deep underground, we're looking at very high temperatures and pressures. They're a couple of kilometres below the sea surface or the ground surface. So how do we reproduce that in the laboratory? What we do is we wrap the piece of rock with some carbon fibre, and we can impose a high pressure. We can pump in fluids at high pressure, and we have a heating jacket with recirculating fluid to maintain a high temperature. And we image all of that, and the wonderful thing about the diamond X-ray source, it's sufficiently bright and penetrative to allow us to look inside at the pore scale. And it is as though we have some wonderful three-dimensional microscope that allows us for the very first time to look at the processes that are happening very deep underground. And we're making a lot of progress towards that. I think we have now a much better understanding of these processes than we did 5 years ago. And this is part of a very long-term program, a 10-year program, funded by Shell and Qatar Petroleum in the Middle East, around CO2 storage and a long-term commitment to understanding these flow processes.